Okay, we've got 15 people. I think we'll get started. Few more people will come in. It's 5 minutes after the hour. So Bill, thank you again for joining, and thank you for your 2 lectures. That's a very good presentation and very useful and resourceful notes. The questions that I have, first, all three have come from Mike Demkovich. First is it correct that if the equation of state of a material is known, one can always calculate its Hugonian for any initial state and shock velocity?
Basically, the answer is yes, but there are some caveats. So this makes the assumption that one understands what phase. If there are phase changes, one needs to know what phase the material is in on the Hugonio in order to be able to do that. And since temperature is not something we normally deal with in shockwave work, obviously, if you know an equation of state and have a complete equation of state where you can get temperature, that allows you to calculate the what phase is stable using the Gibbs free energies, and therefore do that. The assumption that is always made in this business is that the Hugonio state is the equilibrium thermodynamic state. So to the extent that the Hugonio is metastable or out of equilibrium, the calculation will be in error.
Okay, thank you for the answer. The second question is, since a shock is always subsonic with respect to the shock material, can it reflect elastic waves impinging upon it from the shock material? If so, do the reflected waves exhibit a Doppler effect? That is, their wavelength is higher than that of the incident wave.
So that's actually an interesting question. Let me scroll down and find the discussion of wave interactions. So this is the slide that I had concerning wave interactions between two waves, and the discussion here was assuming sort of two shock waves interacting with each other. When you have an elastic wave that is coming in behind, so of course this was a Lagrangian reference, a Lagrangian reference frame, so the material's not in motion here. When you have a second wave coming in, and this actually happens, release waves are, at least the leading edge of a release wave is an elastic wave, and they can catch up with the shock wave, and often do. That is actually what gives rise to the shape of a detonation wave in explosives called the Taylor wave. But what happens, because the shock wave is supersonic with respect to the unshocked material, the elastic wave comes in, it cannot, if you will, penetrate through the shock wave. What it will do is actually modulate the amplitude of the shock wave. When that happens, you get an interaction state at that point. But because it's not actually a material interface, the elastic wave doesn't reflect off the back in the way that you would normally think. And of course, if it does, it would be, if you will, redshifted because the shock wave is receding. But it does set up a modulation in the shock wave, and because of the because of the details of the pressure or the stress and material velocity in the shock wave, there will be a wave, if you will, that feeds back. Because as long as there's any kind of pressure differential, you will end up having a wave that goes back into the shocked material. So, in a way, yes. I never have actually sat down and worked out the equations to do that, for the states, but the same rules as far as impedance matching, the particle velocity and the stress have to be continuous anywhere in the material, except when there's a fracture. And obviously the Rankine-Hugoniot conditions have to be met. Perhaps the hardest part about calculating such an interaction is you will need to understand the wave speed, the compressibility or the Young's modulus behind that shock wave. But from the interaction, the wave that would be D in this case is actually going to be the modulated shock wave, whereas the reflection here would be the reflection of the elastic wave that gives you an interaction state that meets the impedance matching requirements across the boundary.
Okay, thank you. The third question is following up on a comment you made in your first lecture. In viscoelastic material, the speed of sound depends on the strain rate. So the question is, what is the effect of viscoelasticity on shock compression response?
Well, the primary, there are two effects. Obviously, you can have an elastic wave and then what I'll call a plastic wave following it. There may be a time-dependent yielding in the material between those two waves, so that the state, let me go up to right here. So this is an idealized diagram of, in this case, let's call it an elastic wave and a plastic shock following. And in the idealized case, this is a flat top right here. You jump up to some constant stress that corresponds to the yield surface of the material, and then you're constant until the second wave comes through. In a viscoelastic material, because of the viscous effects after the material has failed, so it's sitting on a yield surface, but it's also got a time-dependent, it will relieve stress in a time-dependent fashion. So quite often you might see it jump up and then decay down. A second, of course, issue for that is that in the case of a strong shock wave where the elastic wave is overdriven, the viscosity in the material will tend to broaden the wave. I mentioned on Monday that you can think of a shock wave as a Fourier superposition of an infinite number of states, and those states may have different responses. So you even though a shock wave is, we idealize it as a discontinuity in the real world, they do have some finite thickness, and that is due to viscous effects in the material quite often.
Okay, thank you. We have two more questions that have come up. One is from Yupeng Zhang. This is about how the energy is calculated. So he said in the lecture you mentioned that energy flux is mass flux times the sum of enthalpy and kinetic energy. So which means that energy consists of kinetic part and enthalpy.
Yes.
So why is it that only enthalpy is used to calculate the energy? I think he's referring to the equation, yeah, U plus PV.
Yes. So the reason we only have to deal with, okay, we have to deal with both terms, but the only change is that is put in by the shock wave is kinetic energy, for the simple reason that the shock process is adiabatic. So enthalpy is heat. We don't have time to put heat in. So so whatever happens to the kinetic energy, we have to make a corresponding change in the enthalpy, and really where that comes from is the combination of internal energy and the pressure volume work, which again, because it's work, it's more related to the kinetic energy side of the equation than it is to the heat side of the equation.
Oh, okay, thank you. So can you hear me? Sorry.
Yes, go ahead.
Yes.
Okay, thank you. So I just want to make it clear is that, so basically is that the enthalpy is equivalent to energy, Gibbs energy, Helmholtz energy. So all these energy are equivalent. So the reason we use enthalpy is that because of the variable we can control in these variables convenience, so that we use this enthalpy rather than other type of energy measures.
Yes. This is the formal way. If you go to any of the books that really go into this in detail, you tend to find, or the place you actually tend to find the equations written in this form or in this form are actually in books on gas dynamics that discuss compressible fluid flow. You will see this. But these are fundamental equations. It's total internal energy is that we're dealing with. And so you have a heat part and a work part. So the combination of the change in enthalpy and the change in kinetic energy is the total energy in the system.
Right. Actually, I understand. Yeah, just because this is a fundamental question, because I'm in solid mechanics. So in mechanics, because we are talking about discrete systems, actually, because in this question, also in this shock wave problem, because you mentioned that we consider the materials as discrete, or say as discrete system, that atoms are not continuous. So in this case, may I use Hamiltonian instead of this definition of energy? Just use the Hamiltonian as the total energy for the whole system, so that I can build up a new set of conservation of energy equation for the body.
You can, but fluid dynamics, shockwave dynamics, all those things are the derivations and all are done in the continuum rather than assuming discrete. You can actually derive a lot of the things, a lot of the equations without too much trouble, assuming discrete particles rather than a continuum. It's just that originally, when these equations were developed, they don't really have a meaning if you're down below the continuum level. And so we never really think of them in terms of the being down at the atomic level.
Okay, thank you.
Yeah, next question is from Tadong, and he's asking about additional references where you can learn more about the Lagrangian and Eulerian coordinate system that you introduced in your slides.
I hate to say this, but I'm not aware of a good reference. These are things that I learned by doing it, and learned. I didn't even really learn it in lectures in the courses that I took. But I will look and see if I can find what the best reference that discusses this is, and we'll send Michael Demkovich a list of references that he can then post.
Yes, that would work great. Thank you. I think some other questions are coming in. Oops, where is it? Yeah. Kai Rigi. I have used Extreme Physics by Jeff Colvin and John Larson in the past. So that's a reference. Is this a book? Extreme Physics? Sounds like the name of a book.
Yeah, I'm not familiar with that one.
Yeah, it's a book. There's many chapters, and I remember, I think one or two of them talk about the Lagrangian and the Eulerian things.
That's great. Thank you. Yupeng Zhang's question, the pressure P is a type of normal stress, and the internal energy U contains an enthalpy, contains strain energy. Do we calculate something twice?
No, because the equations as presented are under the hydrostatic assumption. So there's no energy associated with shear strain. It's simply volume strain.
Okay, so if only volume strain, that we also consider, I mean, strain energy is just a two-dot contraction between stress tensor and strain tensor, so that we consider the hydrostatic part of the stress, and in the P term, we definitely also consider the hydrostatic part. So I do not see the contribution from debitoric stress here for the energy. Like of course it's one part of the energy, but the presence of debitoric stress or not, I think should not affect the twice calculation of the strain energy.
Yeah, so the as I pointed out last week, there are stress deviators. The material, it's a solid, it's sitting on a yield surface. So there actually are stress deviators. There is and strain that there is energy associated with that. The general assumption that is made is that the amount of energy relative to the energy in the shock wave is negligible, that the stress deviators can be ignored for most purposes. Obviously, at lower stress, in particular where the material actually exhibits a two-wave behavior because of an elastic wave followed by plastic yielding, giving rise to what's known as the Hugonio-elastic limit, that assumption becomes less and less good. And in fact, I made this statement here. I noted that in an elastic precursor wave, conservation of mass, the same formula applies. Conservation of momentum, because it's still a longitudinal wave, the same equation applies, except for now we're going to replace pressure with longitudinal stress. Conservation of energy gets a little bit more complicated, because now we do have a strain energy that is not necessarily negligible. And for that reason, one needs to be a little careful when working at shock waves that are down in the few tens of kilobars range. I will point out that typically the longitudinal stress when the material is at the yield state is on the order of a few kilobars, rarely more than, say, 15 kilobars. And of course, the lateral stresses are related to the longitudinal stress by the Poisson's ratio. Because the material has strained, the Poisson's ratio may not be exactly the same as what we would measure if we were to go into a lab and do ultrasonic measurements of shear and longitudinal waves. So that's part of the reason I didn't put this in, because there's more to it than just the simple ranking Hugonio equations as normally applied in shockwave work.
Yeah, and Yupeng has another question about plastic flow needs time to develop, where shock wave happens within a few nanoseconds. So how does it develop plastic flow in shock waves?
Okay, so going back to the Hugonio here that shows this, what actually happens is this wave is an elastic wave. This, and it is terminated by plastic yielding. And this is sort of, again, idealized. If you look at a real wave profile, this is not going to be flat. It tends to ramp a little bit. And that's partly because of that. If you look at, well, just about any material that I've dealt with, tin is a good example. This isn't a sharp break. It'll be rounded a little bit and things like that. But things do happen very fast. And that's one of the reasons why I discussed the question of equilibrium. And we can talk about both thermal equilibrium and mechanical equilibrium. The shock wave, what happens in the shock wave sort of is driven by atomic vibration velocities. It only takes a few vibration periods for an atom in a potential well for things to happen. The times when things really get slow is when one has to have diffusion over a few atomic spacings as well. And that actually will cause the shock wave to spread out and for the Hugonio state possibly to be in a non-equilibrium condition for some period of time. And so there will be some time scale for relaxation.
Okay, so basically what you said is that of course, this is a viscoplastic response because it's depend on the strain rate so much. So even though within nanosecond, the plastic deformation can be induced well and noticeable.
Yes.
Okay.
Yes.
Okay.
Yeah. So my background in shock waves is experimental, and I can tell you that in most materials, when you get up to several hundred kilobars, the rise time of a shock wave to a steady state is largely over in a period of 2 nanoseconds. But you will see a little bit of rounding at the top where it takes maybe another maybe 10 nanoseconds for it to go from 95% of the final state to 100% of the final state. And keep in mind that, if this is something like aluminum with a shock wave speed that may be 5 kilometers per second, 10 nanoseconds is actually, that spreads out. That's quite a bit of thickness in the shock wave at that point.
Okay, thank you so much. One interesting question, that how do you determine the onset of plastic deformation in a shock wave test?
Well, really, we determine it by the height of that elastic wave. Once you've overdriven it, well, if the plastic wave is actually going fast enough that it exceeds the zero pressure longitudinal sound speed, the assumption is that plastic yielding is almost instantaneous. Now, in reality, when if you let's hypothetically take an impactor and if I can find the diagram here. If you take an impactor and it impacts a target and you were able to watch what happens as time progresses from the actual time of impact, what you'll notice is that in the case of a situation where there is an elastic precursor, by definition, because the impact is an instantaneous event, you generate a single wave. And that wave will then break up. But the breakup, what you would actually see is as the wave propagates, the amplitude of the wave will actually drop. And you will see another wave with a very large amplitude equal to the initial amplitude start to emerge. But as it emerges, it decays very rapidly to some point where it eventually achieves an equilibrium amplitude. So there is non-equilibrium stuff going on, especially early in the run of a shock wave that's generated by an impact or any other kind of what we would consider to be an instantaneous event. There are a few materials where this behavior is extreme. The one that I can think of right off the top of my head is beryllium. No one has ever seen the elastic precursor in beryllium achieve a steady state, even for run distances of centimeters. And it has been estimated that in beryllium, because the wave speeds are so fast, that the wave may have to run for some distance of meters in order to actually truly be equilibrium.
Okay, Yupeng, you have one more question. Plastic. Yeah, go ahead. You can ask it.
Okay, thank you. So usually for the metals, we say the plastic deformations are incompressible. Usually, I don't know whether this is the case in these shock wave deformations, and also that for elastic materials, usually it's compressible. The Bach modulus it has a finite number. So if we compare these compressible or incompressible materials in terms of shock wave test, do they have any difference in behavior or any difference? Thank you.
Well, shock waves don't admit incompressibility. Shock waves are a consequence of materials being compressible. So we can't really think about incompressibility. When I talk about plastic yielding, that it's a little different from what people normally think of when they do like an MTS machine pull or compression test on something, where they're deforming it, and at some point it does not go back to the initial shape elastically. In plastic deformation in a shock wave, obviously we don't have lateral. We've got lateral confinement by the material itself, so you don't get any spreading. It's uniaxial strain. What actually happens is the normal sorts of situations of plasticity go into effect, but instead of doing what we normally think of, what they do is actually break up the grains that the material is made out of, so that the unit cells rotate and such, and the material relieves that lateral stress, or the deviators really, so that what you end up with is a material that, although at the macroscopic scale it is uniaxially deformed, what has actually happened inside the material is that twinning and dislocations and such allow the lattice to deform in all three dimensions in the materials. And rotation of lattice, rotation of grains, breakup of grains, and rotation will tend to, they accommodate the fact that you can only strain in one direction.
Thank you. Thank you so much.
Yeah, thank you for your question. So I guess we can now go and look at the homework problem solutions.
Okay, let's see here. So, do you see the lecture 4 problem review slides? I wanted to make sure that it's switched properly. Okay, so I gave you 2 problems. One was a relatively simple problem. So if you imagine, a material has a principal Hugonio. So remember, that's one that starts at room temperature and effectively 0 pressure. And you've got some initial density and an intercept and a slope for the linear Hugonio. And it has a thermodynamic Gruneisen parameter that is described by gamma rho as just being a constant. And that is actually quite a common assumption, and in most cases not a bad assumption, at least for solids. It doesn't work so well for liquids. How would you go about calculating the Hugonio of the same substance starting from a different density? And we assume here starting pressure is 0 and there's no difference in the starting energy. Well, if you remember, I actually discussed calculating a Hugonio from an equation of state. And it is that problem. So I'll go down here to this bottom equation. It's the same problem, but our reference curve in this case happens to be the principal Hugonio rather than an isentrope or an isotherm or something like that. So how would we go about doing that? Well, it depends sort of on what you want to do, but if you're trying to calculate a whole Hugonio, so you're going to calculate a series of points and then fit some curve to them or something like that. The simplest thing to do is pick a series of particle velocities on the principal Hugonio. Then you're going to calculate a volume and a pressure and an energy difference that goes along with those and a shock wave speed that go along with those. And now you want to use these values here to calculate your new Hugonio starting from a different density. And for the purposes of this solution, I'm pulling a tilde over the quantities that correspond to the new Hugonio. So what we're going to do, we're still going to use the same volume on our reference compression curve and our new curve, but what will be different is pressure and internal energy. So V naught naught is just the 1 over, this is a specific volume, it's 1 divided by the new density, rho naught naught. And so this term here, we've got the pressure, we've got, I put everything here for the initial statement of this. So an energy of transition, which is 0, we're starting at the same energy. Energy of a reference curve, which is going to be the energy on our principal Hugonio. And the pressure of a reference curve, which is going to be the pressure on our principal Hugonio. And then this, of course, VH over rho H is going to have to obey this requirement here that gamma rho is a constant in our problem. So since we know ETR, the transition energy 0, V naught naught is 1 over rho naught naught, and gamma rho, which is the same as gamma over V, is equal to rho naught gamma naught, we can rearrange that equation to give us a pressure equal to the energy on our principal Hugonio minus 1 over gamma naught rho naught times the pressure on our principal Hugonio divided by the things that were coefficients of this pressure here, V naught naught minus VH over 2 minus 1 over gamma naught rho naught. So everything here is known. That's all principal Hugonio or our starting volume, which we assume we know. And the left-hand side is the pressure. Okay, now we need to know these other things. Well, we just go backwards through things. So here's our internal energy in the shock wave. So we plug in pH tilde, 1/2 of that times V naught naught minus VH, which is also going to be equal to 1/2 times the new particle velocity. That gives us the energy. And then we just rearrange this equation, plugging in the new values to get the shock wave speed. And there we have everything we know. We know UP, we know US, and once we know those, of course, we can fit what would probably be a second order polynomial, so a quadratic. Typically, when you take a linear Hugonio and you do this, you end up with curvature in the new in the new Hugonio, and so you might have to add an extra term in a fit of US versus UP. Now, I had noted in the lecture, if you happen to want a particular point, and really the only thing you can specify a priori is the volume on the new Hugonio, you would first calculate the corresponding value of UP on the principal Hugonio using this, where I've rearranged the volume ratio or the density ratio to get the particle velocity. So that's the solution to that problem. Are there any questions? If not, we'll move on. The second problem, this is actually something that's done fairly often as just a quick and dirty estimate. One can actually do a better job than this, but using a Hugonio, what I call the Hugonio plus Mee-Greeneisen equation of state, in order to get a release adiabat. But this is one that sometimes people use to do a very quick calculation. So if the Hugonio is not a thermodynamic path. It is a locus of end states of the shock process, but the shock process does not actually go along the Hugonio. It goes along the Rayleigh line. But even so, if you take a material that's not porous, so it's full density, so basically its Hugonio is described by the principal Hugonio, that curve in pressure volume space is often quite close to an isentrope or an adiabat, which we assume to be an isentrope. And so people will use the Hugonio to estimate to approximate the isentrope. So the question was, if we make that approximation and we understand that the internal energy change on an isentrope, on our release isentrope, is going to be described by this equation right here. And we assume that it's a linear Hugonio. Let's derive an equation that gives us an estimate of the fraction of the internal energy that was put into the material during the shock wave, and stays in the material after it's released back to zero pressure. Now, if anybody out there is a hunter or likes to shoot, has ever taken a rifle, let's go small, they say it's a 22 caliber rifle, and shot something like a rock, and they go and they find the slug, which is smashed up. Yes, it's had a lot of plastic work done, but you pick it up and that slug, and it is quite hot. That's this energy that we're estimating. So how do we go about doing that? Well, basically the task is to do this integral. We have our Hugonio state here and our final state, which is back at zero pressure. And that's going to be minus the integral from V1 to V2 of P dV. Okay. The way to do this when you have a Hugonio is to start by casting both P and V. And remember, we're assuming, I'm assuming a principal Hugonio right here. So P naught is 0. we cast both of these in terms of the particle velocity. And the reason we do that is we need some way to do this integral analytically. So doing that, P is just what it is. If we differentiate V, we come up with this, depending on, how you go about doing the differential, you might take a few more or less steps to end up to this state. And this actually reduces to this right here. So you'll notice that P is rho naught times US, which is what this is, times UP. Here's rho naught times US here. There's a negative here. So when you take this and you multiply it by that, you end up, and take the negative of it, you end up with this expression for minus PdV. And this is obviously easily integrated. You can do it, you can go look up the integral, or you can actually work it out. The easiest way to work it out is to actually do it in terms of US, and then so you do the variable conversions. But let's assume that we've have done the integral. Here's again what we're doing. We're going from a particle velocity that was on the Hugoniot back to a 0 particle velocity. That corresponds to Hugoniot volume, to the volume at 0 pressure. Actually doing this integral, and notice I've got this as an approximation still. This approximation gives us this quantity right here. It's a logarithm that corresponds to the 1 over C naught plus SUP part of this, and there then is just a linear term that is C naught over S. And I believe, so yeah. Okay, so the original question asked for the fraction of internal energy originally gained in the shock wave that stays in the material. To do that, keep in mind that this is a change in energy going back down to 0 pressure. So we add that to the original energy gained in the shock wave. And we're normalizing that. We're asking for a fraction. So we're going to normalize that. And when we reduce that, we get this as the final value. If you look at the units, wave speed over wave speed squared times wave speed. So this is a pure number. And if you were to go and actually pick some numbers, the limit of this as UH goes to 0, in other words, going back to effectively a infinitesimal elastic wave, the limit is 0. And the limit, if you go to UH being infinite, is 1. So the higher the shock pressure in the material, the more of the internal energy you put in that will remain in the material that when it releases back to 0 pressure. In geophysics, or well, in planetary science, if one is considering, say, impact of something at 20 or 30 kilometers per second, sufficient energy will remain in the material to vaporize quite a bit of it. So this is a non-negligible thing. And that is the solution to that one. Are there any questions about that?
Yeah, please unmute yourself and ask the question. I think we have about 5 minutes remaining in the call. Anyone? Well, if there are no questions, I would like to thank Bill again very much for the lectures and working the problem solutions. It's been very helpful. And thank you very much for taking the time. And thank you to all of you for joining today. And we'll continue the summer school with a new lecture next Monday. Have a good weekend.
Thank you.
Bye now. Bye.